Unit 2, Worksheet 4, Velocity versus Time Graphs and Displacement. Problem 2. From the position versus time data below, answer the following questions. 2A. Construct a graph of position versus time. So we're going to use the information in this data table and plot it in our position versus time graph. So the first thing I'm going to do is I'm going to count up however many boxes I have on my time axis, the x-axis, as well as my position axis, the y-axis. So I need to have for my time going from 0 up to 9 seconds. And for my position, from 0, and it looks like I will have a maximum position of 10 meters. So on my x-axis, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 boxes on my x-axis. Now because I'm going up to 9 seconds, it probably makes sense to go in increments of 1. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 for my last time, which will be measured in seconds. Now this looks like it's going to be a square, so there's probably going to be 10 boxes going up as well. And my maximum position will be 10 meters, so I'll go up by increments of 1. 1 meter, 2 meters, 3, 4, 5, 6, 7, 8, 9, and 10. And then my title is going to be position versus time. So I'm just going to go through and plot my, well, it looks like 10 data points. I'm going to start off at 0, 0. Right down here. Then at 1 second, I have a position of 2 meters. 2 seconds, 4 meters. 3 seconds, 4 meters. 4 seconds, 7 meters. 5 seconds, 10 meters. 6 seconds, 10 meters. 7 seconds, 10 meters. 8 seconds, 5 meters. And my last time is going to be 9 seconds at 0 meters. Now I circled those points because I'm anticipating that, well, it's going to be a bit hard to see once I start drawing my lines to connect these data points. So it looks like I'm going to have a continuous line going through those data points from 0 seconds up to 2 seconds. Then we're going to have one more continuous line from 2 to 3 seconds. Another continuous line from 3 up to 5 seconds. A continuous line from 5 to 7 seconds. Another continuous line all the way down from 7 to 9 seconds. Now, when I say continuous line, what I mean is when I draw those straight lines, if it goes directly through the points, then that's going to be its own time interval where the velocity is going to be constant. And that only works if those lines directly intersect with those data points. So we're going to have 1, 2, 3, 4, 5 regions of the graph with changing velocity. So that's 2A, where we constructed a graph of position versus time. 2B represents the motion with a quantitative velocity versus time graph. Now in order to make this quantitative, I'm going to actually need to figure out what these slopes are going to be. Now I can see that when it's a flat line here and here, I probably don't need to do calculations, and I can assume that the velocity will be 0 meters for every 1 second. But I will need to figure out the slope of these 3 sections of the line in order to give a quantitative value for our velocity. So for the first region of the graph, I'm going to use any of those 2 points on the line just to keep my math really easy, I'm just going to choose the first and the last point for this first region of our graph. Now I don't really have a lot of space here, so I'm just going to write it up at the top, and then I will plot the data points in just a second. So up at the top of the page is where I'm putting for region 1. My velocity is going to be that displacement, the change in position over that period of time. At the end of this region, I am at a position of 4 meters, and that is at a time of 2 seconds. I started off this region at a position of 0 meters and a time of 0 seconds. So my change in position is going to be 4 meters, and my change in time is going to be 2 seconds. When I simplify that, this first region of the graph is going to have a velocity of 2 meters for every 1 second. The second region of the graph right here, we can see is going to have, well, looks like a velocity of 0 meters per second because it's a straight line. But we can also calculate that if we need to. This third region of the graph over here, we can, well, recalculate what that value is going to be. Using my last and point on the line, I'll go with the first again. I'm going to end up at my final position of 10 meters, and that's going to be at a time of 5 seconds. I started off this region at 4 meters and a time of 3 seconds. So this region of the graph for our position versus time has a change in position of 6 meters over 2 seconds, which means the velocity is 3 meters every 1 second. Region 4 of my graph is up here, and it looks like 4 is also going to have a velocity of 0 meters per second. And then this last region of the graph over here, it's that negative slope, so I'm going to use my last point and my first to figure out the velocity in this final region of the graph. So my final position is 0 meters at 9 seconds. I started off at 10 meters, and my starting time was 7 seconds. I have a change in position of negative 10 meters and a change in time of positive 2 seconds. So my velocity for that last region is going to be negative 5 meters for every 1 second. So these are going to be the points that I'm going to have to plot. Region 1, which is representing our position versus time graph there, has a slope of 2 meters for every 1 second. Region 2 of the graph, right over here, has a velocity or a slope of 0 meters per second. Region 3 has a velocity and slope of 3 meters per second. Region 4 of our graph, up here, has a velocity of 0 meters per second. And the last region of the graph, region 5, has a velocity of minus 5 meters every 1 second. So I'm going to set up my velocity versus time graph over here on the right, and I have my maximum velocity in the positive direction of 3 meters per second, and in the negative direction it will be minus 5 meters per second. So when I'm going to be setting that up, I'm going to make sure that my scale is going to be consistent. For my time range, I need to have it set up so it's going to be the same time range that I had on my position versus time graph in order to make this a good quantitative representation of our position versus time graph or plotting the velocities. And because I have still our 10 boxes, I'm going to go with 5 meters per second in both directions. The bottom of the graph is negative 5 meters per second, negative 4, negative 3, -2, -1, and 0 right there. Going up, +1, +2, +3, +4, and +5. These are going to be the axes on our velocity versus time graph. Now what I'm going to do is from 0 to 2 seconds, that first region of my graph, I know that I am going to have a slope on my position versus time graph of +2 meters per second. So on my velocity versus time graph, from 0 to 2 seconds, I'm going to have that solid line. Because I know that in that entire region, we're going to have, well, a velocity of 2 meters per second. In the next region of the graph, from 2 to 3 seconds, it's making it a little bit hard to see. So that first region of the graph, it's 2 meters per second. The next region of the graph, it's 0 meters per second. And I'm going to be using a vertical line to connect these 2 points in order to show that that is going to be a continuous line. The third region of our graph goes from 3 seconds up to 5 seconds, and that's going to have our velocity of +3 meters from 3 to 5 seconds. 3. And I'm going to have my continuous line connecting those 2 points. From 5 to 7 seconds, the velocity is 0 meters per second because the object is not moving. And from 7 to 9 seconds, we have that velocity of -5 meters for every 1 second. So our velocity versus time graph. In the region of 0 to 2 seconds, we're showing we have a +2 meter per second velocity, which corresponds with this region of our position versus time graph. From 2 to 3 seconds on our velocity versus time graph, that velocity is 0 meters per second, which corresponds from a time of 2 to 3 seconds on our position versus time graph with having a slope of 0 meters per second. From 3 to 5 seconds, we have our velocity of 3 meters per second on the velocity versus time graph, and we have our slope from 3 to 5 seconds representing that same number, 3 meters per second. From 5 to 7 seconds, 0 meters per second on the velocity versus time, and a slope of 0 meters per second on our position versus time graph in the same time interval. In the last 2 seconds, from 7 to 9 seconds, our velocity is -5 meters per second, which corresponds with this very steep slope, which has a value of -5 meters per second. Problem 2C. Draw a motion map for the object. Now I have 9 seconds of, data. So I'm just going to go with my kind of traditional way of representing it, where our change in time is going to be each dot is represented by 1 second. I know I'm going to be starting off at a position of 0 meters. So I put my first dot there, and I'm going to indicate that that is 0 seconds. Now on my position timeline up here, the positive direction is to the right, but it looks like I only have 5 ticks. So I need to go up to a maximum position of 10 meters, so I'll make that last one over here 10 meters. So that means each one of these is going to be divvied up into 2 meter intervals. So 10 meters at the very end, 8 meters to the one closer than that, 6 meters, 4 meters, 2 meters, and where we started off at was 0 meters. So if my initial time is 0 seconds and I'm at a position of 0 meters, 1 second later, I'm now at a position of 2 meters from our data table and our position versus time graph. This is 1 second later. I'm going to now add a velocity vector to that first data point, half the length between those 2 points. In order to make my graph a little bit easier to read, I'm going to put the letter V on my velocity vector to indicate that it's velocity. That's pointing from 0 seconds, I'm traveling to the right at a positive velocity, and then 1 second later, I end up at 2 meters for my position. After that, at 2 seconds, I'm at a position of 4 meters. I can now add my velocity vector to my 1 second interval, half the length between those 2 points, add a V to the vector to indicate it's a velocity vector. At 3 seconds, I'm still at a position of 4 meters. And we know from the position line that it's at 4 meters, so you don't need to write down 4 meters. You should write down that it's 3 seconds, though. At 4 seconds, that position jumps up to 7 meters, which will be over here. So my velocity vector is going to get longer, about half the length between those 2 points, with V indicating it's a velocity vector. At 5 seconds, I'm now all the way at a position of 10 meters. I can add my velocity vector again. At 6 seconds, I'm still going to be at a position of 10 meters. I'm actually going to end up moving my label to the right in order to show a bit more space. 5 seconds, 6 seconds, 7 seconds, I am still at that position of 10 meters. At 8 seconds, I'm actually all the way back at a position of 5 meters. So this is going to be a very long arrow. But now it's pointing to the left. Our object is traveling in the negative direction, which is how we're going to end up with a decreasing position and a negative velocity. So that's 8 seconds. At 9 seconds, we're all the way back at our initial position of 0 meters. So this is going to be at 9 seconds, which is where this ends. And one thing that I'm going to do is I'm actually going to add a velocity vector to that endpoint, just to indicate that, well, it is still going to keep traveling in that position as far as we know, even though this is the last point that we actually know, which is where it ends. And then to maybe clarify that our 0 seconds is where we started, we can write down start or the word begins there. So that's how we can represent a motion map from either a data table indicating the times and positions like we have up here, or we could do the same thing by looking at those data points on a position versus time graph like we plotted in problem 2a right up here. So 2c, determine the displacement from 3 to 5 seconds using the velocity versus time graph. Now the way that we can calculate the displacement in a time interval using the velocity versus time graph is by looking at the region between the curve and the x-axis on our velocity versus time graph. So from 3 to 5, we're going to look at this region underneath our curve. So the best way that we can do that is by actually just figuring out the area that there is there. So it looks like we're going to have 2 boxes for our width in that region and 3 boxes for our height. So our height here is going to be our velocity, which is going to be equal to positive 3 meters for every second. And the width is going to be our time of 2 seconds in that interval. Our area here is going to be equal to our sides multiplied by each other. 3 meters per second times 2 seconds. So our area is going to be 6, and because the seconds cancel out, our area is just 6 meters. Now the area is also known as our displacement. So we can write down that the displacement for this region of the graph is equal to 6 meters. We can do the same thing for that next region of the graph from 7 to 9 seconds, right over here. Now this one is going to be a little bit unique because it's actually going into the negative direction and our negative velocity. So it looks like in that region, we're going to have our height of 5 boxes and our width still of 2 boxes. So our velocity in that region is minus 5 meters for every 1 second, and our time interval is still 2 seconds. So the area of that, well, the rectangles, all those boxes between the curve right here and the x-axis, we can calculate to be minus 5 meters per second times 2 seconds. Or that area can equal minus 10 meters. So the displacement here is going to be equal to negative 10 meters. The change in position from 7 to 9 seconds is minus 10 meters. 2F. Determine the average velocity from time of 4 seconds to time of 8 seconds. Now there are a couple of different ways that we can do this. One way is we can look at our velocity versus time graph from 4 seconds right here all the way up to 8 seconds. Now on our velocity versus time graph, we're actually going to have 3 distinct regions of velocity in that region. We have 1 second of velocity of positive 3 meters per second, another region with 2 seconds where the velocity is 0 meters per second, and that last region where our velocity is minus 5 meters per second for just 1 second. We can use that, but another way that we can do that is by looking back at our position versus time graph. Our definition of average velocity is going to be that change in our displacement over that change in a period of time. So we're going from 4 to 8 seconds. So we end up at 8 seconds and we're starting off at 4 seconds. Now we just need to identify the points that correspond with those times. So what position is there at 8 seconds? What position is there at 4 seconds? So at 8 seconds right here, we go up, we have a data point, which right there looks like it's going to be at 5 meters. So the final position in that region is positive 5 meters. And then at 4 seconds right here, if we track that up, looks like we have a position of 7 meters. So the change in position in this region is going to be minus 2 meters, and that change in time is positive 4 seconds. So the average velocity looks like it will be negative 1 meter over 2 seconds, or we can also write that as negative 0.5 meters every 1 second. The average velocity in that region is going to be either of these two answers. By convention, we typically write velocity and speed with the second representation, where it's that change in position or change in distance over every 1 second of a period of time. 2G is going to be the last problem that we have here. It's going to actually be asking for the average speed in that exact same time interval, like problem F did, from 4 to 8 seconds. Now, the difference between average speed and average velocity. Our average speed depends on the path length over our period of time. So our path length, we're going to look to see how far it's traveling in each of those regions. So if we start off at 4 meters, 4 seconds, we are at a position of 7 meters. So 7 meters, it travels up in this region from 7 up to 10 meters. So in 1 second, we have our path starting off with a change of a distance of 3 meters. That next region of the graph, this flat region from 5 to 7 seconds, our change in position and ultimately our change in distance is just going to be 0 meters. And then the last region we'll be looking at is from 7 seconds all the way down to 8 seconds. So we need to figure out not the change in position, but the change in distance from here down to here. If we start off at 10 meters, a position of 10 meters, and we end up at a position of 5 meters, the change in position is minus 5 meters when we are measuring relative to the origin. However, this object still traveled an additional distance of 5 meters. And all of this occurred in those 4 seconds for this region. So the change in distance, or the length of the path traveled, is going to be 8 meters over 4 seconds. So our average speed here is going to be 2 meters for every 1 second. Even though we're still looking at that time interval of 4 seconds to 8 seconds for both parts F and G, we can see that the velocity and speed can result in different values. And that really just comes down to how we're measuring both of these. Velocity only depends on where you start, right here, and where you end up, all the way over here, in that period of time. Speed, however, takes into account your total change in distance, how far you traveled, the length of that path. So if you took a longer route, then that will actually affect your speed. Now, if you took the most direct route between 2 points, and it wasn't like a long, winding road or anything, it's just a straight line between 2 points, in those cases, your velocity and speed can be the same magnitude. But for problems like this, where it looks like this object increases position, then decreases position, well, that change in position is going to be smaller than the entire length of the path, which is why the magnitude of our velocity is smaller than the magnitude of our speed. So at this point, we have now completed the second problem of Unit 2, Worksheet 4, Velocity versus Time Graphs and Displacement.